Sustainability Center of Excellence, and thanks to the active support of Airbus. The topic of ZEROE as the future of aviation is exactly at the crossroads of TBS values and our academic involvement in hot managerial issues, combining aerospace new leap, entrepreneurship, innovation, data science, and of course, environmental commitment. So we're glad to organize it with the support of the TBS aerospace alumni community. I do salute here. And speaking of which, I'd like to introduce you to Florent Rizzo, the president of the Aerospace MBA Alumni Association.
Hello, everybody.
Who moderates this webinar with me, and you will meet him right after the presentation of Matthieu. I'd like to warmly express our gratitude to Airbus, and especially Mélanie Astruc, and of course, our inspiring guest, Matthieu Thomas, lead architect for ZEROE Aircraft program, for taking part to this webinar, enabling us to further understand what ZEROE is all about. But just before, I mean, it's very classic now in webinars, before introducing Matthieu to you, I would like to encourage you to use anytime the chat zone. I saw already some welcoming message, thank you, to ask all the questions you might have. As you're now very familiar with the webinars, you know that Matthieu will address hopefully most of all of these questions during the Q&A session that will take place in roughly half an hour from now. So the ZEROE aircraft has been announced a couple of weeks ago, or even month ago, seen as a clear, loud, and positive signal for the entire aerospace ecosystem in these circumstances. Many questions raised up regarding this very promising initiative. Hence, for us, it's really an honor to introduce you to our guest speaker, Matthieu Thomas, who holds an engineer diploma and a PhD in material sciences. He started his career in working in a small startup on technology transfer before joining Airbus as a thermal engineer working on A350 XWB on multiple aspects like, well, I'll let you talk about that much, but on thermal sizing or in system thermal integrations. And then he moved to the Future Project Office, working on several projects such as the ATR NEO, new regional aircraft, a new single-aisle concept. And now he's the ZEROE lead architect, that is chief engineer role for this pre-program, and work on these projects already since 2018. So once again, thank you all for your participation, and let's fly high with Matthieu. The air is yours. Thank you.
Okay, thanks a lot for the introduction. Can you hear me well first? It's okay?
Sure.
Okay, good. I'm really glad to be with you today for this conference. I have to admit that I'm quite impressed by the number of participants. I've seen more than 100 people in this conference, so it's a really good sign to see that the question of climate change and aviation is important for a future business leader that you are. So it's good. Obviously, the challenge of the climate change is an extremely important topic for Airbus, and that's the reason why we've recently revealed to the world that we have the ambition to develop the first zero-emission commercial aircraft by 2035. So the objective of this conference is to share a little bit of more information on what's behind the ZEROE project, what's behind the scene, to speak about hydrogen, and obviously to speak about what could look like future hydrogen aircraft. So I might have to share now my screen. Okay, and tell me if it's fine for you.
Yes, yeah. It's showing on the screen.
Okay, great. Okay, so let's go. Yeah, let's go. And I will start by giving a little bit of context. The first thing to know is and I'm pretty sure you're well aware of this, is that the aviation industry has set itself very ambitious CO2 target reductions. This target is minus 50% of CO2 emissions by 2050 compared to 2005 levels. If you see my mouse, my pointer, I don't know, just tell me. Can you see my mouse on the screen? No?
Yes, we can see it.
Okay, good.
Yes.
So if you see it, in fact, if we do nothing, we will follow this curve, the top one. So let's say this is the COVID crisis, and obviously the emissions of aviation will continue growing as the traffic growth is increasing. But we know where to go to our objective, which is here. We have three main enablers. First one is the continuous improvements of the technologies which are on board the aircraft, which enable to decrease the fuel consumption of the aircraft. So that's what you see in blue. So there's obviously everything that deals with aircraft operation, optimized operation, including the air traffic management in a range. And then there's the use of sustainable fuel, like biofuel or synthetic fuel made with renewable energy. So this is obviously a major, a big part of the CO2 reduction. So we know all these solutions, and we know that we have to accelerate them to reach our targets. But on top of all this, the challenge is that the story is not only about CO2 emissions. The complete challenge is about the climate impact, which means it's not only about CO2 emissions, it's also the complete greenhouse gases, which are for us CO2 for sure, but also NOx and contrails. And we know that contrails and NOx can potentially have higher impact on the climate than CO2. So it's extremely important to consider the complete picture and not only a part of it, or not only the CO2. So we're conscious about this. We're conscious of this, and we're not the only one. And we already see the evolution of the local regulation. We've seen, for example, in June 2019, the UK, which is the first major economy to pass 2015 net zero emission law, followed by New Zealand, and even in Europe. Europe has stated extremely ambitious targets in terms of greenhouse gases, more than half by 2030, and climate neutrality by 2050. So we see the things evolving rapidly, and it's clear that the societal expectations and the regulation will request aviation to go to zero climate impact. And we believe that the only way to achieve this target is using hydrogen. It's the only fuel for commercial aviation to enable zero emission ambitions. Okay. One point on the renewable energy, which is a very important topic. So why? Because if we want to use hydrogen, we have to use green hydrogen. And green hydrogen is produced with electrolysis. So we use electrolyzers so as to dissociate water into oxygen and hydrogen. And this is risers. So as to operate this process, you need electricity, and you need electricity coming from renewable energies. It's important so as to get green hydrogen. What you can see on these charts is that the renewable energy is starting to scale at an incredible pace. For sure, in terms of absolute terms, they're not at the level all of us want them to be, but the pace of growth is really significant. On the world wind electricity production, it is doubling every 5 years. So here you can see between 2013 and 2018, but it's the same growth between 2015 and 2020. Just that the International Energy Agency has not published this last results. Concerning the solar electricity production, the growth is even higher. It's times 5. And you can even see that, let's say, the slope of the curve is really steep in the end. It's nearly exponential. And that's because even without subsidies, in many regions, renewable energy starts to be cheaper than fossil fuel. And this is obviously a very important aspect in our strategy, since we need low-cost renewable energy so as to produce low-cost green hydrogen, and in the end, to make H2 aviation real. Another important topic is the hydrogen ecosystem. In fact, we need to to track how the hydrogen ecosystem is moving, is developing. So behind ecosystems, there's obviously the states, the nations. There's also the energy producers, the hydrogen producers, and also all the consumers. We're looking at this hydrogen ecosystem since already several years, and what we've seen during the last year is an incredible acceleration of this H2 ecosystem. We've seen, for example, the Japan, which was already since a decade world leader in hydrogen, to state even more ambitious plans for hydrogen, and they even put hydrogen as the heart of their roadmap towards the net zero greenhouse gases by 2050. In Europe, that's the same. The H2 strategy has recently been updated, and it makes clear that H2 is a key building block towards climate neutrality and zero emission economy. That's the same for China, Australia, and some other countries. Then on the demand side, so on let's say the consumer of hydrogen, we also see significant developments. We've seen, for example, last year, 9 different track concepts powered with hydrogen popping up. On the shipping industry, that's the same. And it's interesting because there's many parallels between shipping industry and aircraft. Well, they have both. We have aircraft, we have ports, we have airports, but we have the same kind of operation with point-to-point routes, needing really localized hydrogen infrastructure. So let's say there's a strong parallel between them and us. On the train industry, it has already started. You've seen Alstom already producing some H2 train, and they're moving toward hydrogen because sometimes it's better to. In fact, they still have a lot of train power with diesel, and they would like to decrease their emissions. So one way is to electrify the rails. So, but it means a lot of infrastructure, putting a lot of cables, overhead the trains everywhere. So it's quite expensive, and sometimes, and it's often the case, instead of having this quite complex infrastructure development, it's easier and it's cheaper and it's quicker to move toward hydrogen train powered with fuel cells. So we see already many developments, and it's really important to understand them, because it has obviously a strong impact on the H2 cost, which is critically important for us. In fact, you know, there's no point to develop an aircraft which is extremely climate friendly if it does not achieve any market, and by consequence doesn't have any climate impact. So that's the reason why H2 cost is obviously a key parameter we follow carefully, and you can see on this chart, which is made with several points from several independent institutes, that the hydrogen cost is significantly reducing over time as the demand and the offer is higher, as the production increases, and as the ecosystem is growing up. So that's something we keep an eye on for hopefully a program launch near let's say by 2035. So that's it for, let's say, the content. Let's speak now a little bit of aircraft, and more specifically about the zero emission aircraft. So this aircraft, at least the 2 first one, in fact, when you look at them like this, they look like classical aircraft. But in fact, they're not. There are many differences between the legacy aircraft and this hydrogen aircraft. The propulsion system is different. The fuel system is different. The distribution system is different. The non-propulsive systems are different. There are many differences. And the idea of the following slides is to enter a little bit in the detail to show you what are the differences, and yeah, feel what it could look like in the end. But before doing this, I think it's important to come back to the basics and to understand what are the hydrogen specificities and how the hydrogen specificities impact the aircraft design. So the first thing to know about hydrogen is that for the same amount of energy than kerosene, it is 3 times lighter. So it's obviously very good news from an aircraft performance perspective. Bad news is that it takes more volume to be stored. If we consider hydrogen at atmospheric pressure, ambient temperature, and sea level, the volume you need to store the quantity of energy stored in 1 liter of kerosene would be higher than 3,000 liters for hydrogen. So it's definitely not an option to store it like this in the aircraft. It will not work. One of the options is to pressurize the hydrogen. So if we pressurize hydrogen at 700 bar, we reduce the volume from 3,000 liters to 6 liters. It's typically the option which is considered by the automotive industry. You can see in the Toyota Mirai, they have this kind of H2 tanks pressurized at 700 bar. But for an aircraft, the weight and the volume are, let's say, extremely important, and we do everything we can so as to reduce it. And the thing we can do in addition of this is to liquefy hydrogen. And if we liquefy hydrogen, if we use liquid hydrogen, we will reduce the volume of hydrogen to only 4 liters. That's the best we can do. So obviously we can see already the benefit, but still it means that for the same amount of energy, storing hydrogen will take 4 times more space than storing kerosene. So it will be lighter, but it will take bigger volume. And obviously it will have an impact on the aircraft configuration and on the drag of the aircraft. But we will speak about this later on. So now that we know that we need liquid hydrogen, the question is how to store it. So first element to know is that hydrogen is liquid at 20 Kelvin. So it's minus 253 degrees. It's cryogenic temperature. It's extremely low. And we need to keep it liquid for a long time. So we have, so as to do this, to really limit the heat ingress inside the tank. Why? Because if you have some heat going inside the tank, the liquid hydrogen will start to heat up, then it will start to boil. It will create gaseous hydrogen, so the pressure inside the tank will increase, and we'll have to vent the gaseous hydrogen so as to prevent the pressure to get to really high values. And when we vent the hydrogen, we're losing hydrogen. So it's as if we're losing fuel. It's obviously not a good option for us. So as to store it for a very long time without having to vent it, we need super insulated tanks. And the concept that we think is a good one for aeronautics is this concept that I show here. It's a tank with a double layer, an inner vessel and an outer jacket. And in between these 2 skins, you have a hard vacuum at 10 to the minus 7 bars. So at this pressure, there's nearly no air, so no heat transfers through conduction or convection. The only heat transfers you can have is radiation between the 2 skins. And so as to prevent the radiation, we had some MLI, multi-layer insulation, so as to prevent direct heat transfer from the outer skin to the inner skin. And with this kind of concept, the thermal insulation is really, really high. And we can store liquid hydrogen during many hours, more than 12 hours, without any venting. So this is, let's say, the best solution we find for aircraft. This kind of concepts already exist in other applications, medicines, for example. So our work is to try to adapt them to aircraft studies, to aeronautic standards, making them light and safe for sure. So now that we understand we need this LH2 tanks to store the hydrogen, where to locate this liquid hydrogen tanks? I hope that you will have understood that it's not an option to store liquid hydrogen within the wings. Even if you create really small tanks and you put them inside your wings, the weight penalty will be really too high. So you have to find other locations for VLH tanks. And then there are several options. The first one could be under the wing. That's what we call podded aircraft. So this kind of concept is quite interesting because the liquid hydrogen is really close to the engine. And then for the maintenance, the accessibility under the wing, it's a good choice. But obviously it creates some drag and it puts at stake the efficiency of the wing. So if we would like to keep an efficient wing, we need to put the LH2 tank elsewhere. It can be like here above the cabin, or even after the cabin, after what we call the rear pressure bulkhead. So it's an unpressurized compartment at the rear end of the aircraft. This configuration is obviously quite interesting, especially the caudal, because this aircraft looks like a classical aircraft. So for passenger acceptance, it's good. The tanks are quite accessible, but it has other drawbacks, like you have quite long distribution system of hydrogen. And well, you put a little bit of weight at the rear end of the aircraft, so quite far from the center of gravity of the aircraft, which degrades a little bit the performance. Well, nothing dramatic, but it is always pro and cons in any design. I'm pretty sure you have many other ideas of where to locate the LH2 tank. We have other ones also in mind, and within this phase, which is an exploration phase, we try to figure out what's the best location for these tanks, for example. And it's not only a question of performance, there's a question of maintenance, industrialization of the aircraft. So we look at the problem from many different aspects. Okay, so now that we know how to store liquid hydrogen and where to store it, how to convert it in thrust. Here, there are two big options. The first option is to use a gas turbine, which looks like a classical gas turbine. So that's what we call H2 direct burn. So the gas turbine is similar to the one you have today on the engines, but it has obviously some specificities. The combustion chamber is different, is really specific. The injectors are specific. You have cryogenic heat exchangers so as to heat up the liquid hydrogen to a temperature which is acceptable for the engine. You have many different other components. You have H2 pumps, obviously. So there are many things to be developed. But what is sure is that we know that it's feasible. It has already been demonstrated already quite a long time ago in the 50s by the NASA, from the B-57. Even the Russian did it on the Tupolev. It was in the 80s. So we know it's feasible, and we're already exchanging with the engine manufacturers. And the feedback we have are quite good because they see many opportunities by the use of hydrogen to revise the engine cycle and getting even more performance than what we have today. The second option is completely different. The second option is to use fuel cells. So fuel cells, they do not create thrust directly. They provide electric power, and then we use this electric power so as to power electric motors, propellers, or fan, and then create thrust. I may have to remind a little bit how works a fuel cell. So if I would like to be really simple, a fuel cell is like a battery with an anode and a cathode. You have the hydrogen, which is supplied here, dissociated in protons, so H+, and electrons. But the protons are the only ones which are capable to go through the polymer electronic membrane. The electrons have to go around through a conductor, and these electron movements create electricity. And then on the opposite side, you have oxygen, the proton, the electrons, and you create water with all these components. So the byproduct of the fuel cells is only water. So it's obviously very, very interesting. Moreover, the efficiency of a fuel cell is quite high. It's 50 to 60%. So it's really high, but it has some drawbacks. The weight of the fuel cells and all the systems was to enable to operate them is higher than a classical gas turbine. And the cooling also is one of the problems. They operate at quite low temperatures, so it's quite difficult to extract the calories from the fuel cells and to reject them outboard the aircraft without drag penalties, let's say. So these are the two different propulsion systems, and obviously we can combine them. That was called an hybrid architecture. So in this architecture, you can see you have liquid hydrogen stored in liquid tanks, which feed a gas turbine, okay? And this gas turbine provides most of the power, of the propulsive power, but it is assisted by electric motors, and these electric motors are powered by fuel cells. And the fuel cells are fed by liquid hydrogen. So here you have an heat exchanger so as to convert liquid hydrogen to gaseous hydrogen at the right temperature to operate the fuel cells. And the idea is obviously to take the heat dissipation of the fuel cells so as to enable this exchange. Such kind of architectures is quite interesting because it enables to open new degrees of freedom for the optimization of the gas turbines and increase its efficiencies. There are a lot of different hybridization strategies with low power hybridization strategies or high power strategies. High power, for example, it's boost in takeoff or climb is interesting. Low power, you can have, for example, the assistance during the idle phases. Where you can increase the efficiency of your gas turbine during these phases. Okay, so that's it for the hybrid architecture. And this hybrid architecture is the one that we've selected for the e-concepts that we revealed in September last year. So if I look a little bit to this regional aircraft, I think now you have all the elements in mind to understand what's behind. So you have here the LH2 tanks that provide hydrogen to the fuel cells, which are located here, and also hydrogen to the gas turbines, which are located here. On the gas turbines are the electric motor, which are powered by the fuel cell here. Okay. On top of that, you have H2 refueling system under the LH2 tanks, and you have something here on top of the horizontal tailplane, vertical tailplane, which is H2 safety venting pipes. It's kind of exhaust, so that in case of failure or damage on one H2 tank, we have to vent rapidly the hydrogen, and we vent it here at the top of the aircraft. There are obviously several enablers for an hydrogen aircraft. The first one is performing technologies. So it's really important to have the right technologies and really efficient one. Why? Because this kind of aircraft, hydrogen aircraft, is obviously a little bit penalized by all these different systems in terms of weight. It's also penalized by the additional drag due to the longer fuselage than a legacy kerosene aircraft. So we need to embed inside this aircraft really efficient technology so as to minimize this penalty and potentially even be better than a kerosene aircraft. The second thing on which we can play is the aircraft configuration. So I will take the example of the landing wing body. In fact, this aircraft is quite interesting. So it's interesting due to this aerodynamic efficiency, and it's also interesting in case of hybrid aircraft due to the fact that it lowers the LH2 tank integration penalties. In fact, in such aircraft, you would have the LH2 tank in each part of the cabin, okay, here and here. And if the LH2 tank size is not so high, and so the range of the aircraft is not so high, it can perfectly fit with this free space that you have between the wing and the cabin. So it's a kind of ultimate configuration for the LH2 tank integration. Another enabler, and that's something really important to have in mind, is the product positioning. On these two concepts, you have aircraft with cabin of 200 pax, and you can see that the range is here, it's 2,000 nautical miles, not 3,000 nautical miles, which you could have been expecting when looking at the number of pax. So the reason why we've reduced the range is to limit the tank integration penalties and limit the drag of the aircraft. So by limiting the range, we're increasing the performance of the aircraft. And obviously, by limiting the range, we also limit the capacity of an airline to have some high ranges, and we limit the flexibility. That's it, the flexibility of use of our aircraft. So it's a kind of balance to be to be selected in between aircraft flexibility and aircraft efficiency. And in the end, we may have an hydrogen aircraft having different positioning that were classical kerosene aircraft. Well, high standard for safety and regulations, that's a must. Obviously, there's no debate. New manufacturing capabilities, it's also obvious because we will have new fuel on the final assembly line, for example, and specific airport infrastructure. That's an extremely important point because there's no point in having an aircraft if you don't have the infrastructure developed when it enters into service. So we work a lot already with some airports to ensure that it will be the case. Okay, and there's a last configuration that you may have seen very end of last year. It's the pod configuration. In this pod configuration, the concept is different. Here, this aircraft is only powered with fuel cells, and in fact, you have 6 pods of about 1 megawatt class. That's the order of magnitude for the power. And each of the pods integrates the complete propulsion system from the LH2 tank to the fuel cell, to electric motor, and the propeller. So it's a quite innovative concept that we work on. It's part of the exploration phase that we're doing. So you can see that we don't, let's say, focus on one kind of architecture. We really are open-minded on everything which is possible. Okay, and that's it. I will finish with some key dates. So in fact, all this project has been launched, in fact, already, yes, in 2018, 2-3 years ago. Last year, it has been moved toward a pre-program launch. So it's really official, and we revealed it to the world. We're already quite a big thing looking at it from all the different perspectives. There's obviously the team working on the aircraft design, there's the team working on the ecosystem, on the economics, on the value for an airline, on the climate impact, on the industrialization, manufacturing, airport, safety, all the different aspects are covered. And we take time for defining what is the best concept, what's the most resilient concept for the uncertainties we have in the future. What are the key technologies we need to develop, take time to develop them, demonstrate that it's feasible, and then once we'll have done this, by 2025, select the product and go toward an entry into service, which should be before 2035. So that's it for this presentation. I think it was the last slide. I'm pretty sure you have some questions. I hope you enjoyed and you learned things. Try to be really transparent and let's say make a really accessible presentation for all of you. So now I'm really happy to answer to the question you may have.
Thank you very much, Matthieu. Indeed, there are a lot of questions that pop up in the chat zone, but I'll let Florent moderate the questions. So thank you so much for your presentation. Thank you.
You're welcome.
Yeah, sure. Thank you very much, Matthieu. That was a really interesting presentation. And yeah, we do have a lot of questions in the chat. I think one of the key challenges regarding hydrogen is the possible impact on the storage and the impact on airport infrastructure to store this massive quantity of hydrogen which is required. So, and it echoes to some of the questions we get also from the participants. How do we incorporate these operational constraints into your project? And is there any collaboration with airports which is planned in order to facilitate the deployment of the ZEROE aircraft?
Yeah. So yeah, exactly. I think the answer is yes. We are taking these questions of operation on how to operate an H2 aircraft extremely seriously. Our intent is not only to focus on the aircraft, is to have a look to the complete ecosystem, and the airports are obviously part of it. So yes, we are working with some airports to understand what does it mean to have hydrogen on an airport? Can we have a hydrogen hub, which could be an airport where the aircraft could be refilled, but also be used. Hydrogen could be used for many other applications in the airport. So there's a question of what kind of development strategy could be defined. It's a question of safety, of security, of place where to locate all these elements. So we're discussing obviously with all this. There's a lot of questions on what could be the impact on the people who will have to operate the hydrogen aircraft in terms of training, in terms of certification. Even the firemen will need some specific training for this. So we're obviously looking at all these aspects, and we're obviously very well supported by the airports, and also not only the airports, but the people who are really operating the aircraft, the ones who are making the services. We will, for example, also need some specific ground equipment, GSE, so as to refill our aircraft. So we're discussing with some GSE manufacturers so as to define how can we develop them, what kind of interfaces between these specific components in the aircraft and these components in the airport. So all these questions are clearly on the table, and we work quite hard on them, because once again, it's really important to secure the infrastructure development for the entry into service. If not, no, we could have an aircraft without the infrastructure. There's no point, you know.
Indeed. Thank you very much, Matthieu. Also, we got some maybe more technical questions, but that could be interesting also. One of them was, how do you think of a process in the engine to extract hydrogen during the flight itself? This was a first interesting technical question. And there is another technical question, is the following one. Is there a way to make the hydrogen solution that can have a higher boiling point without affecting neutrality of the fuel emission?
Okay, I'm not sure to have understood the first question. Can you repeat it, just to be sure I will capture it?
Do you think there is a process for an engine to extract hydrogen during the flight itself?
To extract from?
I guess it's from the sky itself. Or
you mean? Okay.
Yeah.
Okay, from the external air. So in fact, you don't find hydrogen like this in the air. You have hydrogen which is generally combined with other components, and the most simple one is the water. So as to do it, it's an electrolyzer. So it's just the opposite of a fuel cell. Fuel cells, you know, you have hydrogen and oxygen, and you create water and electricity. And an electrolyzer is just the opposite. You put water, and you have in the end hydrogen, oxygen, and electricity. And you need electricity. So it's not possible really to extract from the air hydrogen. Another option could be to store water, for example, in the aircraft, add electrolyzers, power it so as to create hydrogen, and then send it to the propulsion system. But this would be most probably extremely expensive in terms of weight and quite complex. A thing that we've had a look to is to because there are some options anyway, which consist in using aluminium plus water, and in fact there is a kind of chemical reaction between aluminium and water which creates hydrogen. So we had a look at it with some research lab institutes in the US. The conclusion is that it's extremely heavy, and it's really difficult to manage the reaction time of such reactions. So it was not finally a good option. Well, but for sure, we're exploring different options. For standing, we have identified some, the one that we showed to you, but there might be some other options. Why not?
Okay, thank you, Matthieu. There was also a question regarding this new concept. One of the concepts you have described is the blended wing body aircraft, or which looks like a flying wing, basically.
It is.
And which is very innovative in civil aviation. How did you come up with this concept, which is very different from the two other concepts and which are pretty much really conventional?
Sure. So blending wing body, as it makes a long time that these concepts exist. There are some which are flying, but not in civil commercial aviation. So why? Well, there are many reasons for this. For sure, it's a concept which enables to have a very good aerodynamic performance. But in terms of industrialization, in terms of family concept, for example, if you need to increase your blending wing body, but it's not easy with an aircraft produced like this. Even to operate, it's different. So it's so radically different from our aircraft that it's really difficult to put it on the market. Then, if we think about hydrogen aircraft, things are changing. We have to think differently. That's the reason why we say maybe the shift toward this kind of aircraft configuration is interesting, because when looking at hydrogen or LH2 tank integration, this concept is a really good one, because it minimizes the drag impact resulting from the LH2 tank integration. It's really minimizing it. It's probably the best concept for LH2 tank integration. So that's the reason why we believe that we have to speak about it and work on it, because it's really promising.
Okay, thank you. And I know that in order to develop such projects, you have been working on, you have to change your working methods for the implementation of such type of aircraft, and using such type of agile methods. Could you tell us more about that?
Yeah, so definitely. In fact, we are in an exploration phase. It means all the ideas are welcome. We need to go very quick, and we need to connect the people together. It's not only a question of aircraft design. It's not only a question of propulsion design. It's not safety. It's all the different aspects, including the business, including the aircraft operation, including the economics, all industrial, everything. So we really tried to impulse new ways of working, which make the people collaborating in a much efficient manner. And so we had a look to the different ways of working in the companies, which I've tested, and we found in the end that the agile method was really the most appropriate for the phase we are today. So we started with a very small team in agile method, and we're trying to scale it up. And for the time being, we were quite successful in having it. People really felt empowered. They really think, they really believe and see that their work has an impact on let's say the exploration, on even on our decisions. And we really try to ensure that the people who are doing have some power to decide how to organize, to decide how to do it, etc. So we give, for example, as a lead architect, I give the main direction, etc. But how to do it exactly, my team is deciding. So they really are engaged, involved in this project. And yeah, it's a really pleasureful working to work on this topic, as you can imagine.
Okay, I see. Yeah, and I guess that flying a ZEROE aircraft in the future will have an impact on the complete ecosystem. And when you consider these different projects, what will be the possible impacts on the passenger experience, for example? Or maybe it will require new skill for the pilot and for the maintenance and for the rest of the ecosystem around the aircraft. Any views regarding that?
Yeah. So passenger experience if you only change the propulsion system and hydrogen, it should have no major impact, except the fact that the passenger would be really proud to fly in an aircraft which does not have any climate impact. But let's say it will remain aircraft, it will fly at the same altitude, blah blah blah. It's no big difference for pilot. Well, there might be a little bit of specificities in the fuel management, in the propulsion management, especially for all the all-bodied version, but nothing. Let's say no big changes. It will remain, let's say, an aircraft. For the operation, what is sure is that we try to minimize the impact of the on the operational side. We could put a lot of burden on the operations on the airport, for example, but we don't want to do this because this aircraft has to be compatible, and especially in the early phases, with all the other aircraft that will still operating. You will still have in the early phases some aircraft using sustainable fuel, for example. So let's say you can't have completely different procedures, completely different elements. So we try really to make it as simple as possible and as close to operate to a classical aircraft.
Okay, I see. And I think we had a set of questions on the performance, also on the engine that will be operated for such type of aircraft. What, according to you, is the technology readiness level of these projects and the level of maturity, basically, of this project?
Yeah. So the TRL level, technology readiness level of fuel cells in aeronautic is relatively low because it has never flown. So there's only some it has flown on very small aircraft, but not on big commercial aircraft. For the gas turbines, that's the same. It has flown in the 50s. It was a demonstrator, but let's say it was not something which was optimized for performance and so on. So there are a lot of technologies to be developed. So the current technology readiness level is lower than 3 for the time being on all this technology, and we will try to learn about them, develop them in parallel as we are exploring. And when we will have to decide what the concept we want to be, we want to make these technologies, the one that we have selected, will have to be at a TRL level, which is about 6. When you decide what aircraft you would like to launch, the technologies generally have to be around TRL 6. So that's what we target. And so that's the reason why, in parallel to the exploration stream, we are working a lot on the technology development internally, but also with many suppliers, with the engine manufacturers, with some partners. So that's a big stream of activity, including demonstration, so ground demonstrations, so as to see that it's really feasible and to learn a lot really rapidly. And in the end, we even plan to make flight test demonstrator to reach the highest level of TRL, so which means putting let's say the technology, the new systems in real operating conditions, in real make real tests. You see, not only ground tests, but real flight.
Okay. Another question is regarding the range of such type of aircraft. Will it be possible to have a zero emission aircraft for longer flights in the future? And another related question is, do you think that in the long run, the complete fleet will shift to hydrogen aircraft, or there will be a mix of classical, I would say, engine aircraft and ZEROE aircraft?
Okay, so for concerning the long range aircraft, that's a very interesting question. In fact, well, the long-range aircraft are really penalized by the quantity. So if I take a kerosene aircraft, or classic legacy aircraft, long range, they are quite penalized by the fact that you need a huge amount of fuel, and this fuel is really heavy. And in the end, you even put a little bit of fuel so as to create the fuel you will use in the end, at the end of your flight. So it's a massive penalty for long-range aircraft. When you switch to hydrogen, the weight of the fuel is significantly reduced. And you can even see on very long-range aircraft that the what we call max takeoff weight, so the maximum weight of the aircraft, is decreasing compared to a kerosene aircraft. So that's obviously something which is interesting, and there's no showstopper in having hydrogen aircraft or long-range aircraft. You might have, sure, a little bit of drag penalty due to the tank integration, so additional energy consumption. But well, there is no showstopper for the time being to use hydrogen for long-range aircraft. It can be adapted to any kind of aircraft. And then for sure, at one point in time, there will be, especially at the beginning, a mix of aircraft, just like for the cars industry. You have electric cars, hybrid cars, and gasoline cars. I mean, it's a kind of transition that we'll have to do. It's impossible to replace all the current fleets suddenly like this. It's not possible. So yes, we'll have to live for a certain period of time with a mix of aircraft, hydrogen and ones using sustainable fuel.
And did you have feedbacks or remarks from the aircraft operators, airlines, or lessors regarding this new concept?
Sure, they're really interested in.
Okay.
Really, I can't reveal the details. I can't reveal with who we're speaking to, but the general feedback is obviously like all of us. They see this societal expectation coming, the regulation changing, and they're asking themselves, where do I have to invest? What are the next steps? What can I do for enabling zero emission flight? So yes, for sure, they're extremely interested in what we're doing and eager to know exactly what we can propose them.
Okay, thank you. Another question, you talked about large hydrogen tank. Is there any experience of a large hydrogen tank as the one which was mentioned in the presentation? Yeah, so
well, in fact, in some other industries, you have even bigger electric tanks, but generally they're static. But for spatial, they also have quite big. For launchers, have quite big electric tanks. So it's not that's a big problem to have a quite big electric tank by itself. No, it's already existing in other industries, but for sure we have to adapt them to our specificities. So high level of safety standards, that's for sure. Light, maintainable, etc.
And okay, there is another interesting question about retrofitting. Would it be possible to retrofit an actual aircraft to make it use this type of engine, or do you have to go completely in line fit and when you go to market with this technology?
Yeah. So. Well, retrofitting is maybe a little bit difficult, but making forward fit of an aircraft, I understand the point is, for example, we remove the gas turbine, we remove the fuel system, and we had the electric tank, and for example, the gas turbine burning hydrogen. That's probably the question which is behind. Yes, it could be an option for sure, and we're also exploring these kind of things.
Okay.
There are some pro and cons. In fact, when you design an aircraft. So when an aircraft has been designed for kerosene application, it has some constraints, some limits. It has maximum design weight. It has some specific volumes, and you have to adapt your H2 systems to fit within these constraints. So it's obviously less optimum than a new aircraft, but it might be a little bit cheapest and more straightforward. Or quicker if we'd like to do something. We are obviously looking at this, yes.
Okay. Christophe, do we have time for more questions? 2 minutes? Okay. Maybe there is a question that we got asked several times. It's about safety, and either any safety issues regarding to the use of hydrogen, and which may imply additional constraints for the flight.
Yeah, I really understand this question. It's an important.
Yeah.
The first thing to know and to remind is that the safety standards in aeronautics are really, really high, and there's no compromise on it at all. I think, yeah. Well, you know, we make a lot of things. We have certifications. We have a long process, and I think it's one of the safest transport means we have in the world. So there's no debate about this. So now the question is, if we shift from kerosene to hydrogen, can it degrade the safety? And the answer is no. There's no point. It's not an option. Okay. So we will have to do whatever it needs so as to have the same level of safety. For sure, the fuel properties are different. Mm-hmm. For sure, you need less energy to ignite hydrogen versus kerosene. But we will take the specific precautions so as to prevent any problem and to ensure that the safety levels are kept. So you will need specific sensors, you will need specific valves, we need specific systems for sure. We'll have to develop them and prove that they're safe, but there won't be any compromise. It will be at least at the same level of a current aircraft and maybe even more safe. So there's no compromise on safety in our aircraft, that's for sure.
Safety stays #1 priority.
Sure, yeah. You can't trade safety.
Really interesting. Maybe really last question to end this conference. What would you recommend for the young graduate of Toulouse Business School if they want to be involved in such type of project? Do you have any advice for them or topic of interest for them? What would you recommend them?
Yeah. First, come as you are. I mean, it's really important. We need people with different views. Diversity is really important in our project because we need new ideas. We need people being really fresh in their mind. So and you can even see there's a lot of young people working within this project. The most important thing, it's a feeling, is to have very strong competencies in one specific field, to be really, really accurate in one topic, and then put this knowledge at the service of the whole team, and be really open to share your knowledge, to put your work, to share your work with the others, and to enable very good collaborations with others, which will have other competencies, other viewpoints, and that's where there's a little bit of magic, but that's where the team starts to be really, really strong by adding all these different competencies and people being really open-minded to others' views. So that's the only recommendation I will have. Develop some specific competencies and then be open to collaborate with the others.
Specific skills and stays open and to stay open, really important. Exactly. Yeah, it's really great to end on those words. Maybe Christophe, I'll let you take the last word for this conference.
Yes, thank you very much, Florent, for the moderating this conference. I would like to warmly thank you, Matthieu. Honestly, we couldn't cover all the questions, so I have a final question to you, Matthieu. Would it be possible to, we will wrap up all the remaining questions and pending questions. Yeah. Would it be possible to share it with you and maybe afterwards get some views, answering to this, and then we can share that with the community that is currently online, because probably there is a frustration because there's so many questions about competition, about how the hydrogen might be produced, would be involved in it, and so there's so many questions.
Yeah.
So
I understand.
Thank you very much, because you've been very sharp in your questions and you cover a lot of things. But you see, it's almost unlimited the subject. So we'll warmly thank you for that. and we can reassure as well our community. So there is a lot to do in this field in the future, and for sure that will be further presentations as well on other projects. So thank you all for attending this session. Everything will be available online. So all of you who have been connected, you will get the link very fast after this presentation. And we thank as well Matthieu because he accepted to share his slides. So thank you for that. We'll display these slides to you. Thank you all. Thank you again.
Thank you very much, Christophe, Laurent, and all the participants. It was a great pleasure for me to be with you, and I really appreciated this exchange. Thanks a lot, and bye-bye.
Bye-bye.